Hello students, we are going to look at the 2021 H3 Chemistry Paper 1 question 1, which is a stimulus based question. So as per all discussion, before we do a stimulus based question, it will be good to look at the stimulus. So for this particular stimulus, if you look through the whole passage, it's about environmental conservation, that is. Okay, so the first line actually tells you about the concern over the increasing concentration of CO2 in the atmosphere due to the burning of fossil fuels. You guys would have done some of these things in your usual tutorials, so I don't think it's something that is alarming. Okay, and then it's being described that for the first abstracts, there are two possible methods of capturing CO2. So if you have done the specimen paper, this would be quite similar. I'm not sure if it's exactly similar, but it's not something that is new to you regarding the capturing of CO2 from the atmosphere, regarding where you can subsequently use for recycling. And then for abstract 2, it's describing a method for recycling captured CO2 into methanol. So this is like a conversion to a useful raw material, which can be used as a fuel. And then later on, they mentioned that the process needs to be designed so that the chemicals and catalysts are recycled in a closed loops so that no pollution occurs. Some of the key provided to you includes like what exactly is ppm. So it's parts per million by volume. So they are very explicit here, by volume. And then they also mention what is GT, which is called gigaton. So mention 1 gigaton is 10 to the power of 15 grams. Okay, so the first abstract is abstracted from Energy and Environment Science 2012, quite an old paper. If you look through it, they talk about the current concentration of CO2 is about 120 parts per million higher than the pre-industrial value of 270 parts per million. So it was mentioned that the increase is the result of the accumulation of additional 600 gigatons of CO2, okay, in the atmosphere from human activities. At the current rates, human activities add an additional 15 gigatons of CO2 per year into the atmosphere. So these are some of the important details you might want to take note of. And then they describe process 1 with some energetics data, which I will not go into details. Okay, so we'll come to them when we need them. And then for process 2, you have some more energetic data, but in particular, if you look at reaction 6, okay, it is some sort of a hydrolysis kind of reaction in which this particular functional group known as a carbamate is being hydrolyzed to give you an amine and bicarbonate. Okay, then it was mentioned that CO2 can be recovered in the concentrated form by heating the mixture of carbamate and hydrogen carbonate to 85 degrees Celsius. Okay, so apologies that sometimes I will call hydrogen carbonate as bicarbonate, because that is the common name. And then for abstract 2 is taken from Chem Society Review. This is quite a good review journal from the British Society of Chemistry or related, or Royal Society of Chemistry, sorry, I beg your pardon. Yeah, okay, so over here the article describe methods of converting CO2 into methanol. Okay, so again, energetics data given to you. They show you a particular compound or two compounds. TMP is a secondary amine, okay, and then of course you have BQ3. So Q is actually this thing known as pentafluorophenol group. Okay, so it's bonded to the boron center. Okay, and then it was mentioned that in the first stage of the process, TMPBQ3 promotes the heterolytic cleavage of molecular hydrogen. Okay, so this is quite important because the heterolytic cleavage of molecular hydrogen actually provides the hydride, okay, which later on could be responsible for some form of reduction. Okay, so again, we are not sure. When I say we are not sure means that as a student, when you're reading this at this instance, you might not be very sure what exactly is going on, but it doesn't really matter. Yeah, because the key thing here regarding this heterolytic cleavage means that my HH, right, becomes a H plus and H minus. Okay, so of course it will not happen on its own. It must be driven by the presence of in this case a catalyst. So that was what's described above. Okay, and then moving on to the last bits, you were given the overall process for the conversion of CO2 into methanol by 8 reactions, is shown in figure 1.3. Okay, so this is figure 1.3. Right, okay, so this is a little bit complicated. Maybe I should provide some explanation before we move on to the question proper. Okay, so in the beginning, this is not new. It was actually described above over here, okay, in equation 8, the heterolytic cleavage of molecular hydrogen. Okay, and then in the process, give you this. Okay, and then you notice that when CO2 is being introduced into the system, okay, if I can just sketch this out a little bit, right, so BQ3, right, is actually a hydride equivalence. It's not a hydride, but it's hydride equivalence. Okay, so there's a negative formal charge at the boron. So you notice that the hydride kind of perform some sort of like a nucleophilic attack on the CO2. Okay, it's not very obvious, or it may not be entirely correct. Actually, it doesn't really, again, doesn't really 100% matter here, but based on your limited knowledge of H2 and H3, of course, regarding the realm of chemistry, you might be predicting something like a nucleophilic attack by this hydride. Okay, so that is how this H ends up to be here. And then of course, because it's some form of a nucleophilic attack, the oxygen gain a negative charge, and of course it doesn't exist as O minus, so the minus now coordinates to a boron center, and that's why there's another -1 formal charge at the boron center. Okay, and then after that, I introduce A. So what exactly is A? Okay, anyway, A is not given, and of course B is not given as well, so they are unknown. Probably later on we need to identify what they are, so let's not panic too much for now. Okay, so when A was introduced, and then you'll notice that this thing sort of continues. Of course, here we can kind of easily identify what A is, because you notice that the difference between this, there's a BQ3 with a minus here, and then this BQ3 with a minus is in this position, and then later on when A is being introduced, you notice that it becomes a BQ3 minus as well. So I can from here predict that the likely identity of A is BQ3. Yeah, just simply by just recognizing the pattern. Yeah, so that's about it. And then after that, of course, I have a BQ3 minus from where? Actually, it's from here. Okay, and then it will then donate another hydride. Okay, it's the same process. Donates another hydride. Okay, and then become BQ3, and then this is another form of nucleophilic addition. Okay, so again it's the same thing, so BQ3 with a hydride equivalent over here, and then it performs a nucleophilic attack at this carbonyl like carbon, and then I push the electrons to neutralize the charge over at the oxygen. So now I'm getting this, so you can see that it's being reduced with 2 hydrogen, and then this thing continues. What exactly happens here is that it donates a H plus. So now the H plus being donated, right, it's donated to BQ3 minus with the O here. That's why it come out as an OH group. Okay, So why does it come out as an OH group? I think you can sort of predict that what exactly you are expecting to happen here is something like this. I'm just going to show you a very simple kind of arrow pushing. Okay, so with a lone pairs of electrons here, I can push the electron density in to form this particular pi bond. Okay, so I'm going to erase this sign. Okay, so I push the electron density in, okay, to form that particular pi bond, and then at the same time I will grab a H plus from here. Okay, so where does the H plus comes from? The H plus actually comes from here. Okay, so if you really need me to draw everything out, I could do that. Okay, so because it's not 100% correct to represent it like a H plus. Okay, so this thing will actually look like this, with an N and of course a H and a H. So it's not exactly a H plus, but it's a protonated secondary amine. So I'm going to grab this H and then of course neutralize the charge, and then this is what I'm going to get. Okay, I just double check the structure, make sure it's correct. Yes, it's correct. Okay, and then I'm going to get this, and then after that what's going to happen is that this whole thing is going to undergo some form of acid-base neutralization reaction. How do we know? Because this whole species remains. Are you able to see that? Okay, this whole species remains, and then after that TMP is being ejected out. BQ3 is being ejected out. So what is being left behind is just H and OH. So from here I can easily guess that my B is H2O. Okay, you can easily verify that, and I believe it is asked in one of the questions later on, and that's about it. Okay, so we are pretty much done, okay, with analyzing the data in the stimulus. Okay, so this particular stimulus isn't that difficult to understand. I hope you appreciate that. Alright, so I'm going to move on to the question proper. Okay, so we are supposed to use the data in abstract 1 to estimate the total volume of the Earth's atmosphere in cubic meter. So from your calculation, assume that all the atmosphere is at RTP. Okay, so right now let us try to fish out the data we need. Okay, so from the data we recognize that the 120 part per million increase is the result of the accumulation of the additional 600 gigatons. Okay, so we will use this particular piece of information, okay, to first calculate the increase in the number of moles of CO2. Okay, so this will be equals to 600 gigatons, so that will be 600 times 10 to the power of 15. Okay, and then divide by the MR of CO2, so that will be 44, and then from here we're going to get 1.364 times 10 to the power of 16 moles. Okay, so if you punch your calculator quickly, that's what you're going to get. For the next mark, we are required to estimate the total volume of the Earth's atmosphere in cubic meter. Okay, so before we perform the calculation, we just let the total volume, okay, volume be V. Okay, then we take a look at the information given to us over here. So we were told that the 120 parts per million increase is the results of the accumulation of an additional 600 gigatons of CO2. We understand the definition of the meaning of parts per million. So that means that if it's 1 part per million, that means that if we let 1 part be 1 cubic meter, yeah, so the total volume we are looking at will be 10 to the power of 6 cubic meter, or 1 million cubic meter. Yeah, so that's the meaning of 1 part per million. Yeah, if the total volume is let's say larger, so for example it's not 1 million cubic meter, but it's 10 to the power 7 cubic, or 10 to the power 7 cubic meter, then we are not looking at 1 cubic meter for one part, but we're looking at 10 cubic meter for one part. Yeah, so that's the meaning of parts per million. Yeah, so if you go by simple logic. Okay, so from here, if we let the total volume be V, then what we are going to do here will be based on the number of moles of CO2, so that will be 1.364 times 10 to the power of 16. We're going to multiply by 24 to convert it to dm cube, and then we're going to convert it to cubic meter by multiplying by 10 to the power minus 3, because remember that 1 dm cube is 10 to the power minus 3 cubic meter. And then we're going to divide this by the total volume, that is the Earth's atmosphere. Yeah, because from this particular division, we are going to get 120 parts per million. Yeah, so because we are doing it in cubic meter, so that would mean that for every 1 million cubic meter, 120 cubic meter will be CO2. Yeah, so this is the logic behind it. Then if I rearrange and let V be the subject of the equation, I'm going to get 2.73 times 10 to the power of 18 cubic meter. So that would be my answer. Okay, and then of course later on there's a part which asks us to calculate the expected annual increase in parts per million of atmospheric CO2 from current human activity. So over here we were told that at current rates, human activities adds an additional 15 gigatons of CO2 per year into the atmosphere. So we are going to use the same logic. Okay, so that would be the current increase in number of moles of CO2 per year. Okay, so that would be 15 times 10 to the power of 15 divide by again 44. So I'm going to get 3.409 times 10 to the power of 14 moles. Okay, and then from here we are going to calculate the expected increase in CO2 in ppm. So remember that for ppm we need to do some conversion. Okay, so based on 3.409 times 10 to the power of 14, so we do the same thing. We convert it to dm cube, we convert it to cubic meter, and then we divide it by the Earth's total volume calculated in part A, so that will be 2.73 times 10 to the power of 18. So remember that this is 2.73 times 10 to the power of 18 cubic meter. So the calculation here, right, we are getting our answer based on whatever volume in cubic meter per 1 cubic meter. Yeah, but now we want to look at parts per million. So we don't want to do it in we don't want to do it in per cubic meter. We want to do it in per 1 million cubic meter. That's the reason why we want it to be in ppm. So that is why from here we need to multiply by 10 to the power of 6. Okay, and then from here a quick calculation will reveal the answer to be 3 parts per million. Yeah, so as simple as that. Okay, and then for B part 2, we were asked, or we were told that the current annual increase or average annual increase in atmospheric CO2 is approximately 2 parts per million. So you realize that it is actually 33% lower. Okay, you were asked to suggest a reason for the difference in figure. So you are expecting 3 parts per million, but what you are getting is 2 parts per million. So that's a good thing. Why is that the case? I think there are many reasons you can give. So for example, you can say that okay, so because of climate change, I think recently you read about there's a COP 27 happening in one of the countries in Africa, I think. Yeah, so because of that, then awareness of climate change allows human to actually cut down on the consumption of CO2. Okay, yeah, so because of that, then so perhaps we are not expecting people to use or to produce as much CO2 as possible. And then of course, how do we cut down the amount of CO2? Then perhaps we are looking at renewable sources of energy, such as using solar cells or wind turbines. Okay, and of course, because of awareness of climate change, we might, or certain areas in the world might be planting more trees to absorb the CO2 being released, and because of that, the increase in CO2 is lesser than expected. Yeah, so there could be a lot of reasons you can give. So any reasons related to climate change, I think, can help you score a credit for B Part 2. So unfortunately, the answers, you cannot get it from the passage. You probably just need to infer from your general knowledge. Okay, then moving on to Part C, which I believe is a relatively straightforward calculation. You are asked to calculate the value of delta H4, okay, which is over here. Yeah, so if you look at this whole series of equation from equations 1, 2, 3, and 4, right, you'll notice that if I were to sum up everything, okay, so for example, if I sum up equations 1 and 2, I'm going to cancel off the sodium hydroxide on the left of equation 1 and on the right of equation 2, and then I'm going to cancel sodium carbonate solution. Okay, and then what's going to happen is that calcium carbonate will also be cancelled off if we were to add in equation 3. Okay, and of course CO2 will be cancelled off as well. Yep, and then what are we left with? We are actually left with calcium oxide solids and H2O liquid on the right hand side, and calcium hydroxide solid on the left hand side. Okay, but what we want for equation 4 is actually the reverse of what we want from adding equations 1, 2, and 3. So that means that we should be summing up equation 1, 2, and 3, but in their negative form. Means you multiply equations 1, 2, and 3 by -1, or you swap the product and the reactant. Okay, so with that, we can easily determine delta H4. Okay, and that would be delta minus delta H1 minus delta H2 minus delta H3. Okay, if you just quickly punch your calculator, you should get negative 64.5 kilojoules per mole. Okay, so this should be quite straightforward. Okay, and then moving on to part D. By comparing the energy requirements of process 1 and 2 described in abstract 1, suggest and explain which process is more favorable. Okay, so for process 1, we are looking at negative 64.5 kilojoules per mole. Okay, and then of course for process 2, we can only understand it from equation 5, which involve a release of 155 kilojoules per mole of equations, okay, in terms of energy released. Okay, and then the question actually asks us by comparing the energy requirement. So we are asked which one is more favorable. Okay, so are we able to tell from the delta H, is this a reasonable approach? Probably not. Yeah, because question is asking us from the perspective, okay, of energy. Yeah, so this is very important because we need to be able to look at what we need to do to allow the process to be taking place. Okay, so if you take a look at process 1, we are required to decompose calcium carbonate, okay, by heating it to 700 degrees Celsius. Yeah, so take note of this. Yeah, so it's a highly endothermic process. Okay, so in that case, I'm actually introducing a lot of energy into the system to drive out the production of CO2. Okay, right? Okay, so we are supposed to compare the two. Okay, so what about process 2? For process 2, you are basically mixing up. Okay, I mean, when reactor is CO2, they form the carbamate, and then after the carbamate is being formed, and then it will be hydrolyzed. Okay, and then of course here you will mention that the CO2 can be recovered by heating the mixture of carbamate and hydrogen carbonate to 85 degrees Celsius. So the temperature requirement is less harsh. Okay, so in that case, our conclusion would be we prefer process 2 because it's more favorable, and I can recover the CO2 simply by heating the mixture of carbamate and hydrogen carbonate to 85 degrees C. Process 1, I need to heat it to 700 degrees Celsius. Okay, so in terms of energy requirement, process 2 is less harsh. Okay, yep. Then for part E, we are supposed to draw a mechanism for the reaction described in equation 5. Okay, so this wouldn't come as too much of a surprise because after all, H3 is an extension of H2, so you are required to do some mechanism drawing. Okay, so I'm just going to draw it over here rather than over at the space over here, because I think it's easier. Okay, so again, I'm going to showcase CO2. I'm also going to showcase the partial charges. Okay, and then I can draw my RNH2 here. It has a lone pairs of electrons which can act as a nucleophile, so it will perform a nucleophilic attack on the carbonyl carbon, and then electron density will be pushed towards oxygen by breaking the pi bond. Okay, and then of course along the way I'm going to develop a formal charge on the nitrogen, and then of course the carbon here I have COO minus. Okay, and then what's going to happen here is that I do expect some form of acid-base neutralization reaction to take place with the conjugate acids, okay, of this particular amide, and then in the process I'm going to produce the carbamates. Okay, sorry, it's not amide, it's carbamates, huh? And then of course I'm going to get the conjugate acid of the primary amine, okay, as required by the question. Okay, so this is a very simple mechanism drawing, that's why it's only 1 mark, 1 step. Okay, so that's the key step. And then for part F, for the production of methanol from CO2 shown in equation 7 to be sustainable, so let's take a look at equation 7. Okay, so equation 7 is over here. Okay, to be sustainable, a renewable and readily available source of H2 such as hydrogen must be added. So you will ask suggest a sustainable method of obtaining H2 from water, explain your choice. Okay, so what we can do is probably some form of electrolysis of water using solar energy, or we can use a photocatalyst. Okay, the reason being our sunlight is a viable source or reliable source of energy. We get it daily, and about 70% of the Earth's surface is covered with water. Okay, so the production of H2 from water is likely to be sustainable. Okay, so I'm just going to verbalize some of these thought process because you probably don't need me to write them down. And then suggest or use a bond energy calculation to estimate the energy required per mole of H2 for the method you described in F1. So first of all, we need to be able to write out a balanced equation, and then in the process I get H2 plus half O2. Okay, and then of course energy required per mole of H2. This is simply what are we breaking here? We are breaking 2OH sigma bond, so that will be 2,460 is endothermic breakage. Okay, and then of course the formation of HH bond it releases negative 436 kilojoules of energy, and then oxygen because there's only half mole, so I just take half times 496. Okay, so over here we're going to get positive 236 kilojoules per mole of energy. Yeah, required to produce 1 mole of hydrogen gas. Okay, and then from here you're supposed to use your answer to F2 and equation 7 to calculate the overall energy change for the conversion of 1 mole of CO2 into methanol. Okay, yep. So can we do that easily? I think the easiest way is perhaps maybe to write out some form of a balanced equations. Hopefully that is going to help, because ultimately we are looking at CO2 plus 3H2 to give us methanol and water. Okay, so what we can do here is we're going to rewrite this equation: CO2 gas plus 3H2 gas. Okay, I'm going to get methanol OH liquids plus H2O liquids. Okay, so I'm expecting this to be negative 131 kilojoules of energy. Is it? Yeah, it's given here. This negative 131, so I'm going to get negative 131. Okay, and then what's going to happen here is that the easiest way we might want to do it might be actually to draw out some form of a cycle. How does that help? Well, I mean, in the nature of the question in F part 2, right, requires us to actually perform this calculation. So why not we leverage on this to actually produce the H2 which we need. Okay, so that will be this particular step. Okay, I don't have space, so I'm just going to write over them. So this will be 236. Okay, 236 times 3 moles of hydrogen produced. Okay, so in this case, on top here, because CO2 gets carried over, so CO2 will remain as CO2. Okay, and then of course plus 3H2O liquid. And then in the process, I'm going to produce an additional O2, which is 3/2 O2. If I introduce it here, I must also introduce it here. Okay, because it's not harmful. I mean, it's not going to cause any misconception. And then this is the one we need to calculate, delta H. Okay, so this is essentially just 236 times 3 minus 131. Okay, so this equals to plus 577 kilojoules per mole. Okay, so I hope the explanation so far has been okay, because some of these concepts I do agree that it can be a little bit difficult to understand. Okay, so for part G, the method described in abstract 2 uses this particular compound TMP-BQ3. Suggests why the substituents on boron in BQ3 have been chosen to be C6F5 rather than C6H5. Okay, so how do we understand this? Okay, so first of all, right, we need to be aware that we need to be aware of the difference in the property of this group. Okay, I'm going to just highlight in pink this group. Okay, versus a normal benzene ring. Okay, like this. Yeah, so what is the difference? Excuse me. Now, fluorine is the most electronegative element known to mankind. Yeah, so now I have 5 fluorine group bonded to the phenyl ring, so it does make the phenyl ring overall electron withdrawing. So if we make it electron withdrawing, that will make the boron center highly electron deficient. Okay, so making it highly electron deficient thus allows it to act as an extremely strong Lewis acid, so much so that it might be able to explain why the heterolytic cleavage of molecular hydrogen is possible, because it will make even a very unpolarizable hydrogen molecules to be polarized, and this will result in heterolytic cleavage. Yeah, so this is the key idea you need to be able to appreciate. And of course, upon polarization, you form this HBQ3 minus, this particular anion, and this particular anion has a negative charge, formal charge at the boron. With the electron withdrawing group, is going to stabilize the boron center. That is something you have to be aware. Remember this: withdrawing group stabilize negative charge, donating group, or rather withdrawing group stabilize negatively charged center, or center that are electron rich. Donating group stabilizes positively charged center, or center that are electron deficient. So this is the kind of logic we are looking at when we are dealing with a question like this. Okay, so I hope that explanation helps. And then of course for part 2, TMP is more basic than piperidine. You are given the structure of piperidine. I think we can easily understand why. Do take note that some students might have the misconception that TMP has more electron donating group. Now this is incorrect. Okay, it doesn't have more electron donating group. The number of electron donating group remains as 2. Okay, as exemplified by the LQ group over here. Oops, sorry, I'm just going to use a highlighter. Over here and over here. Yeah, so if you compare it with piperidine, the number of electron with donating group is the same. Yeah, what makes the difference is the steric demand, okay, imposed by the 4-methyl group, okay, or 2 on each side, okay, on TMP. Yeah, the steric demand being imposed, right, or the steric hindrance for that matter, right, okay, will actually allows the conjugate acid of TMP to be more stabilized. Yeah, because it makes it less likely to be deprotonated. That is the main idea you need to be aware of. Okay, so with that, I think we have basically answered part G. And then of course for part H, not to forget a mechanism drawing. Draw the mechanism for the reaction shown in equation 8. You may represent TMP as R2NH in your description. So equation 8. So again, you need to show this polarization. So again, we're going to just draw it in one step. Okay, so what I'm going to do here is I'm just going to show this. Okay, R NH2, so it's R. Okay, so this is N here, and then another R group here, and then with a H here, the lone pair, and then of course I have hydrogen, and then hopefully hydrogen will be polarized by my boron center, okay, to form some sort of a sigma complex. Okay, now for simplicity, because of polarization, I expect hydrolytic cleavage to happen. So this is likely to take place and attack the boron center, and because of that, it will induce the attack of the electron deficient hydrogen ends by the secondary amine. And then of course, in the process, I'm going to get R2NH2 plus, and then of course plus HBQ3 minus. Something like this. Okay, but do take note that this is not likely to be the actual mechanism. The actual mechanism is likely to be one involving the hydrogen, or rather the molecular hydrogen, forms some sort of a sigma complex with BQ3, and then in the process it induces a partial positive charge at the hydrogen end, which results in a nucleophilic attack, or you can call it an acid-base neutralization, some sort of a reaction before the end that is sigma bonded to the boron is being directly bonded to the boron after in the course of a reaction. Okay, so that is likely to facilitate, this process is likely to facilitate the hydrolytic cleavage. The formation of sigma complex is likely to lead to a weakening of the HH bond as well. Okay, and then of course moving on to part I, try methylamine and boron trifluoride reacts readily with each other. So again, this is a new reaction, but it's going to give you some hints to the question later on. State the type of reaction shown in equation 9. This is basically a Lewis acid-base reaction. It's not a normal Bronsted acid-base. Why? Because there is no H plus introduced. The so-called Lewis acidic center is a boron center. Okay, and then suggest why TMPBQ3 does not form a NB bond as in equation 9. So again, you might be curious, why is it that when I add TMP with a lone pairs of electrons over here, it doesn't attack the boron center? Why is that the case? Well, I mean, there are two important reasons. Number one is, remember I mentioned earlier on that TMP is sterically hindered at the secondary nitrogen center due to the 4 methyl groups. And then of course the boron center here is likely to be hindered by the presence of the 3 pentafluorophenol group as well. The pentafluorophenol group is not likely to allow the structure to retain as a flat structure. Okay, it's likely to be kind of tilted like a like the blade of a fan, you know, like it's kind of like having some 3-dimensional shape. It's not perfect flat surface. Okay, yep. So that explains for part 2. And then of course for J1, I then suggest the identities of substance A and B. We have already identified them. Okay, so for A is BQ3, for B is H2O. Already explained when I was explaining the stimulus. And of course for part 2, reaction 8 occurs in 2 steps. Construct a balanced equation for each of these steps. So we're looking at equation 8. So where is equation 8? Yeah, equation 8 is over here. So it occurs in 2 steps. Okay, yeah. So of course in the process, methanol is being introduced. Okay, so what is likely to be the 2 steps? Okay, so first of all, I expect again the oxygen center to be protonated. Okay, because that will be the simplest idea of all. Because if I don't protonate the oxygen center, then it's difficult for BQ3 to be released, because in the process of releasing BQ3, the oxygen center will be the positive charge will be neutralized. So that is likely to be the process we are talking about. Okay, so I'm not going to write my answer here. Okay, I'm just going to jot down what I've discussed earlier on above, so you know what I'm talking about. Okay, so the 2 steps. The first step is likely to be TMPH with a plus charge. Okay, and then of course plus this methyl group H, and then with O, BQ3 minus. Okay, and then arrow, I'm going to get TMP plus perhaps CH3, just going to write it out, O, and then H with a plus charge, and then BQ3 with a minus. Okay, and then of course the final step will be CH3 OH with plus charge, BQ3 with a minus, and then of course I'm going to end up with CH3OH plus BQ3. Okay, so if I add up the 2 together, I'm going to end up with whatever was mentioned, like this with this. Okay, give me methanol and BQ3. Of course, in the process, TMP will also be released. Okay, so that will be the end of my review to question 1 of the 2021 H3 chemistry paper.